Hello friends, in this video we will discuss about restoring division method. This is one type of division method which is used in computer architecture and organization. There are two types of division methods. The first one is restoring division method. Second method is non-restoring division method. In this video, we should discuss only about this restoring method. In the next video, we should discuss about non-restoring division method. Now, what is meant by restoring? To understand this restoring concept, let us take one example of division. If the dividend is 10001011 is dividing with 1101. Now, this is a binary division we are going to perform. To understand this binary division, let us take one decimal division first. This is 215 is dividing with the 3. Now let us start the division process. Here only one digit in divisor, here 3 digits in dividend. First let us start with the 2. Here when we see the first digit, it is not divisible by 3 because it is the lesser number. So that we have to take one more digit along with 2, 21. So 3 divides 21 in 7 times. That means 21 is the product. Then we should subtract these two values. Then the remainder is 0, 0. Next, you should take the next digit 5. You can skip these two leftmost zeros. Now again divide 5 with 3. Then it divides the 5 in only one time. That means 3. Again we have to subtract this 3 from 5. Then it gives the remainder as 2. Here you can observe that here whenever we are applying the negative sign, that means the divisor is having negative sign. That means it becomes as a minus m. M means this is the divisor m, this is the dividend d. So when we apply the negative sign, this m becomes as minus m. Minus m means it doesn't mean the 2's complement value of m in computer method. Similarly, here also minus m. Now let us come to the binary division. This is the dividend. It should be indicated with the D. This is the divisor indicated with the M. The number of bits are 4, so that at a time we have to see 4 bits to divide this dividend with the help of divisor. Now 1101 means its equivalent value is 13 in decimal equivalent. Here 1000. First let us see 4 bits. Its equivalent is 8. So 8 is not divisible by 1101 because this is the lesser value. So that you have to take next bit also. Now after taking the next bit, it becomes as this is 16 plus 1, it becomes as 17. So that now it is divisible by divisor in one time only. So 1, then it becomes as 1101. Now subtract this value. 1 minus 1 is 0. This is 0. 0 minus 1 is not possible, so that we have to take the borrow from this one. Then it becomes as 2. 2 minus 1 is 1. Then it becomes as 1. It should be reduced by 1. So its value is 0. 1 minus 1. Now it is reduced by 1. Then it becomes as 0. Now you can skip the leftmost 2 zeros. The remaining bits are 1, 0, 0. Now you should take the next bit only single bit at a time, 0. It is 1, 0, 0, 0. Again, it is not divisible by 1101 because this is the lesser value. Its equivalent value is 8 again. But in manual method, directly just by inserting the 0 in the quotient part and take the next bit to perform the division. Okay, but the computer doesn't know how to perform the manual method. Okay, so, but it follows the regular method just by subtracting the divisor from this remainder, partial remainder only. That means here just they should write the 1101 applies minus, that means subtraction. But it is not correct method. So only we have to restore this value to add next bit along with these 4 bits. So how can we restore this 1000 at this place? Just by adding one more m at this place. This is minus m. When we added with the plus m, the summation will become as 000. Okay, it doesn't change the value. That means by just by adding the m, we can get the restored value as 1000. And now we should place the 0 at this place. And take next bit along with these 4 bits. Then it becomes as 1. Now its equivalent value is 17. Now it is divisible by 1101 in one time. Again 1101 we should write here. Again subtract. 1 minus 1 is 0, 0. Again it is 2, 1. It is 1, 0. This is also 0, 1. These two we can skip. Now the next bit is directly it should take it as 1, 1, 0, 0, 1. Here again the same procedure, but here no further bits are there in dividend, so that we can stop the process. This is the final remainder. Okay, so this is the method which we are using with the restoring concept. Understand? So what we have observed in this division part, every time in the partial division part, we are performing the subtraction of the divisor. Subtraction of divisor means what? We are adding the dividend with the 2's complemented value of the divisor. Again, here what we observed here, we have restored the value when the remainder is less than the divisor if the dividend has further more bits. So to restore the data, we have to add plus m. This is the second step. Clear? Next, after restore the value, we have to insert 0 and take the next bit to perform the division. Clear? So this is nothing but restoring concept. Now use this concept to perform the computer method of division. Now you should see the restoring division method. Let us take one example. Divide 8 by 3. Here 8 is the dividend. In binary 1000, 3 means divisor indicated by m. 3 equivalent to binary is 0011. Always we should take equal number of bits for both dividend and divisor in this restoring computer method. Now here we should take the 2's complemented value of m, because in every partial division we have to perform the minus m. Okay, we have to perform the subtraction of the m from the dividend bits. Already we have seen. Okay, that's why I have written the 2's complemented value means m dash plus 1, 1's complement plus 1, which is equivalent to minus m. Now minus m means the sign bit is 1, and whenever we are using the minus, we have to take the 2's complemented value of the magnitude bits. The 2's complemented value of magnitude bits are 1, 0, 1, 1. So 1, 1, 0, 1. Okay. Next, the count. So how many cycles of divisions, partial divisions we have to perform for this computer method? Count size. Count which is equal to n. That means the number of bits in divisor. Here, depending on the number of bits used in the divisor, we should follow the number of partial divisions. Okay, that means n equal to 4. Next, A means which is the accumulator register used to store partial remainder and also to store the final remainder at the end of the process. Now coming to the restoring division algorithm. Already we have seen in the previous example. Here we have 3 steps. We have to perform these 3 steps in n number of times depending on the number of bits in divisor. The first step is shift A and D slash Q left 1 bit position. Subtract M from A and place the answer back in A. The third step is if the sign of A is 1, set Q0 to 0 and add M back to A, that is restore A, otherwise set Q0 to 1. These are the 3 steps we have to follow to perform the restoring division algorithm in computer method. Now let us see the process of division. This is the first column, operation, type of operation we have to perform. Next, this is the sign bit of the accumulator. This is the accumulator register. Here D slash Q means at the beginning, in the initial stage, we have filled this register with the dividend bits only. During the process of division, we should fill the quotient bits also starting from right side, LSB side. The LSB of the quotient part is indicated with the Q0. And the last column is count n. Count n means the partial cycles we have to perform are n number of cycles. Now, according to the first step, shift A and D slash Q left 1 bit position. So here D slash Q means in the beginning we stored the dividend bits. At the end of the process, the total number of bits in this register stores the quotient bits. Okay. Now shift A and left 1 bit position. That means the total bits A and these bits should move towards the left side. That means 0, move to this place, 0, 0, 1, 0, 0, 0, 0. The leftmost bit will went out. Okay, it should be cancelled. Next, the rightmost bit, this is empty space, so that you should place an empty box. This box which is ready to store the quotient bit of the LSB position. According to the second step, subtract m from a. This is for every partial division we have to perform. Already we have seen there. Okay, in the previous example, subtract m from a and place the result answer back in a. That means the second step is subtraction. Subtract means we have to add the 2's complemented value of the m to the previous accumulator. That means a minus m. This is the subtraction of m from a. That means what? A plus 2's complemented value. Of course, it is subtraction operation, but here we are performing the accumulator values are to be added with the 2's complemented value of the m only. What are the 2's complemented values of m? These are the 2's complemented values of m already available. Now we should use these 2's complemented values. Just add 1, 1, 0 with carry 1, 1, 1, 1, 1. Now you should check the value of the sign bit. So the second step is completed. Now let us come to the third one. If the sign of a is 1, set q0 to 0 and add m back to a, that is restore a. What does it mean? The resultant, the addition is 1. 1 means what? Negative signed. Negative signed, when it comes negative sign, divisor is greater than value than the dividend part. That means what? When it happens only during the restoring process. Okay, during the restoring only, the resultant, that means the remainder should have the negative sign number. Okay, so if the remainder is a negative sign, we have to place the 0 in the quotient part of the LSB. Okay, and what we have to do, this should be restored by adding the plus m to get the restore value of a itself, previous value. So restore means add m. M means what are the bits? 0, 0, 1, 1. Simply they have written only 2 bits. Okay. So 1, 1, you can write both zeros also, no problem. Okay. It doesn't change the value when we add zeros. Okay. Now we should add 0, 1, 1. 1, 1 is 0 with carry 1. 1, 1 is 0 with carry 1. Again 0 with carry 1. Again 0 with carry 1. This is one more extra bit will come. This here we are using the 2's complement method. The leftmost carry is called as a ignore carry. Okay, you can delete it. Now let us see the sign bit value. This is positive sign, and the remaining bits also you can check. The same accumulator values should be restored back at this place. Okay, 0, 0, 0, 0, 1. Both are same values. Okay, now already we have inserted this is a 0 according to the set q0 depending on this sign bit value. So with this the first cycle of the process is completed. Okay, now let us move to the second cycle from this stage. Again you have to follow the same 3 steps. First initial step is shifting operation. What is shifting? A and q. Okay, A and D or Q, whatever it is. So A bits are these bits, and these bits we have to move towards left side 1 bit position. 0, 0, 0, 0. Next 1, 0, 0, 0. This will cancel. Okay, and one more LSB bit should be empty. Okay, this is a empty box. Now again subtraction operation. Subtraction means we have to add the 2's complemented value of m to the accumulator values. So after shifting, this is the accumulator value. Now we should add the 2's complemented value of m. Then the result is this one, 1, 0 plus 1 is 1, 1 plus 0 is 1, 1, 1, 1. Now again you should check the sign bit 1. 1 means what? You have to restore it. How can we restore? By adding the plus m bits. Okay, that means 1, 1. Okay, and place 0 in the LSB position of quotient again. Okay, so by adding these 2 bits, the result sum is this one. With this, the second cycle is completed. Okay, and also one more point is here, n is initially it is 4 because the number of bits in divisor are 4. At the end of the first cycle, this should be reduced by 1. That means 4 minus 1 equal to 3. After completion of second cycle, it should be reduced again by 1. That means 3 minus 1 equal to 2. Again, after end of the third cycle, it should be reduced by 1. That means 1. Again, it should be reduced by 1 minus 1 equal to 0. In this way, this value should be reduced for every cycle. Okay, now we are at a third step, third cycle. Now again shifting operation. Shifting means A and Q bits should be shifted towards left side. Okay. Next subtraction operation. After subtraction only you have to check the sign bit value. This is 0. That means the dividend is completely divisible with the divisor. Okay. Then you should place 1 in the LSB position of quotient. Okay. Now here no need of restore the previous remainder value, right? So with this the third cycle is completed. Okay, now with this only the third cycle is completed. Now let us move to again shifting operation. Next subtraction operation. Next set q. Set q means depending on the sign bit only we should place. Here it is 1 means you have to place the 0 at this place and you have to restore the data by adding the m. Okay, then the resultant is, this is the result. Now you should check what is the value of n. Here we reach to fourth cycle. At the end of the fourth cycle, the n should become as 0. Now we should stop the process and check whether the answer is correct or not. How can we check? Here the accumulator is used to store the partial remainders and also the final remainder. That means at the end of the process, the bits in accumulator are remainder bits. And this is a quotient register having the quotient bits. Okay. Now how can we cross check the answer? This is the process of verification. This division process continues until n equal to 0. Already completed. Verification. You should multiply quotient with the divisor plus remainder, which is equal to dividend. Okay. From the above result, what is the value of remainder? 0, 0, 0, 1, 0. Its equivalent value is 2. Similarly, quotient value 0, 0, 1, 0. This is 2. Again, now we should substitute these remainder and quotient values and divisor values in this. Okay, Q 2. M means divisor. Divisor is 0, 0, 1, 1. Its equivalent is 3. Plus remainder is 2. 2 into 3 is 6 plus 2, which is equal to 8. This is the equivalent dividend value. So this is the division of two numbers using restoring division method. Thank you.